The sound barrier. We often hear this phrase, but rarely think about what it really means. Today, we'll explore what sound actually is, how planes first reach supersonic speeds, and what really happens when a plane crashes into sound. First, let's clarify. What is sound? Sound is a mechanical vibration of an elastic medium, such as air. Imagine a piston pushing into the medium. As it moves, it displaces the nearest molecules. The molecules themselves hardly travel far. They simply pass the push to their neighbors. This creates alternating regions of compression and rarefaction that propagate outward as a wave. It is this pressure wave that reaches our ear and is perceived as sound. The speed of sound depends on the properties of the medium through which it travels. In denser substances, molecules are harder to move, and sound travels more slowly. But the more elastic the material, the faster the particles return to their original positions, and the faster the wave propagates. In gases, the decisive factor is temperature. In air, density and elasticity are linked, so their effects cancel out, leaving temperature as the main influence. The higher it is, the faster sound travels. For example, in air at 20 degrees Celsius, the speed of sound is about 343 meters per second. In water, it is around 1,500, and in steel, it is nearly 5,000. Thus, sound is the boundary speed at which a pressure wave propagates through a medium. During World War II, American pilots came closer than ever to the edge of the sound barrier. The Lockheed P-38 Lightning in a dive could reach speeds of about 0.8 Mach, dangerously close to the aerodynamic limits of that era. But what exactly happened when it approached this threshold? As the aircraft accelerated, local supersonic zones appeared over the upper surface of the wing. In these regions, shock waves formed, drastically altering the airflow. This speed is commonly referred to as the critical Mach number. The shock waves caused the airflow to separate from the wing's surface, making it unstable. As a result, the center of pressure shifted rearward. This led to a significant loss of lift, disrupting the aircraft's balance. At the same time, the tailplane experienced the opposite effect. Due to the altered pressure distribution, its lift actually increased. This forced the aircraft's nose downward into a steep dive, while the controls became unbearably heavy. Attempting to pull the P-38 out of such a dive was almost impossible. The aerodynamic loads on the elevator were so extreme that no pilot's physical strength was sufficient to overcome them. Many Lightnings were lost in these conditions. Entering a dive was easy, but recovering from it without a large margin of altitude was nearly impossible. A solution emerged after a series of studies conducted by Lockheed engineers. One of the first to scientifically explain the problem and identify its cause was the American aerodynamicist John Stack. He demonstrated that the key to recovery lay in controlling airflow and reducing the load on the tailplane. Eventually, the P-38 was equipped with special dive recovery flaps. These devices created additional drag and redirected the airflow under the wing, stabilizing the aircraft and restoring controllability. From that moment on, pilots could safely recover from dives, even at transonic speeds. After the war, engineers sought to understand, could it be possible to consciously and safely break the sound barrier? The answer came in the form of the Bell X-1, a small experimental aircraft designed specifically to cross the speed of sound for the first time. Its fuselage mirrored the shape of a .50 caliber bullet, as such projectiles had already proven their stability at supersonic speeds. This design allowed shock waves to be separated and prevented them from disturbing the airflow around the aircraft. The X-1 was also equipped with a rocket engine, bypassing the limitations of piston engines and ensuring steady acceleration. Its wings were made thin and short to reduce aerodynamic drag. They no longer sliced through the airflow. They slipped smoothly through it. The control system was radically reinforced and redesigned. Engineers understood that near Mach 1, air behaves differently. The elevator loses effectiveness, and aerodynamic forces respond with a delay. On the X-1, controls remained responsive and stable even while passing through zones of sudden pressure changes. On October 14, 1947, test pilot Chuck Yeager lifted the X-1 under the belly of a B-29 bomber and ignited its rocket engine at an altitude of 13 kilometers. The aircraft began to accelerate. 0.92 Mach. 0.99 Mach. And suddenly, the instruments registered Mach 1.06. Thus, the Bell X-1 became the first aircraft in history to successfully break the sound barrier. It was observed that as an aircraft approaches the speed of sound, air behaves differently. Pressure in front of the plane rises rapidly, and the atmosphere itself becomes an obstacle. As the aircraft nears the speed of sound, the pressure waves that freely spread forward at subsonic speeds begin to compress in front of the nose. Air molecules cannot move out of the way fast enough, and their compression forms a compression front. At the moment of transition, this front transforms into a shock wave, a sudden jump in pressure, forming a Mach cone that trails the aircraft. To pass through this cone is to pass through the sound barrier. The aircraft literally pushes through its own pressure waves. On the ground, this moment is heard as a loud clap, a sonic boom. A sonic boom is not just sound. It is a pressure front capable of causing significant damage. When a Mach cone reaches the ground, its trace forms a hyperbolic pressure wave, which can rattle windows, vibrate walls, and even shatter glass. In the 1960s, during the Operation Bongo 2 test series, thousands of residents in Oklahoma City reported damage caused by sonic booms. Afterward, passenger airliners were prohibited from flying faster than sound over land. Supersonic flight was allowed only over the ocean. Today, engineers are working on the concept of quiet supersonic flight. For example, the NASA X-59 is designed so that the shock wave is distributed differently, transforming from a sharp boom into a soft hum. If these technologies succeed, supersonic passenger travel could become possible again, but without destructive effects.